I just have to change gears mentally a little bit because prior to this teaching this one, I teach the algorithms course, and it's so different that I realized that it's interferes with my ability to cover this stuff.
Not to mention, whenever you're in person, you get to walk from classroom to classroom.
Oh, I didn't think about
transition time.
I didn't think about that. It does sort of clear your mind. But
yeah, exactly. It gives you transitions.
But like, if I can just say this, because some of you guys will probably drift towards programming, or something involving programming, something like that. And there's something about there's this problem of the maximum. The longest increasing subsequence in a sequence. And I know that probably in 320 this was addressed, or 326, but that's really interesting because the code is just a few lines, but it's so hard to figure out what it is doing. And so you think about that problem. You have a sequence, a finite sequence of numbers, and you want to find the longest increasing subsequence of that. Okay, can I show you this just real quick? It's really very interesting. Just take a moment. Just want to wait till the rest of the people get here. I was trying to convince my son, who's taking a course in C at Santa Monica College, to be interested in it, but he totally missed it. He doesn't get the subtlety of it. So let me just give you. So 2 minus 5, 3, minus 6, minus 7, 10, and 4, say. If this is your sequence, what is the longest increasing? There might be more than one, but what's the longest increasing subsequence? Or give me an example. How long is it? And give me an example of it. Okay, somebody just got here. They're probably all confused. So I'm looking for, what a subsequence is, right? They taught that in 320, right? So you want to find a subsequence that's increasing, but the longest one possible I just threw down these numbers here, but how long is it? What's the longest subsequence you can find increasing?
From looking at it, I think 3 times.
Yeah, could you give me, so what did you find? 2, 3, 10 or something? Or was another one?
And then I just kind of kept checking a few others. -5, 3, 10.
3, 4 is another one, right?
Yeah, or -5, 3, 4.
So are you familiar with the profundities of this? I mean, if you have a sequence of length 2n, did you know that there's a theorem that there must exist an increasing subsequence of, or a decreasing subsequence of length n plus 1? Are you aware of that? This is a classic thing that gets taught in 320.
No, this is news to me.
It's an Erdős. Paul Erdős proved that. But yeah, go ahead. Did I cut you off? I'm sorry.
I'm just trying to apply it. So if you've got a sequence of length 2n, so an even number, then it has
let's do it. Can I?
Sure.
So what should I put here? Not to cheat. I don't want to be a cheater. That's not going to help. Doesn't make it interesting, right? So how about minus 1? Okay. So this is 8, right? So according to that theorem, there's longest increasing or longest decreasing of what length? 3, right?
N plus 1?
Sorry, n plus, yeah. So this is 2n, so n plus 1, right? So in that case, would be what? N is, so 5. I don't know. Now I'm nervous. Now I'm quite nervous if I got the theorem right. Because n is 4, right? I don't see it. Uh-oh. Maybe I got the theorem. It's embarrassing. It's a Tracy Whittem theorem, but I don't. It's something like this. So this is saying that, okay, I'll have to research this. So I do not see, in fact, I don't even see a 4. Can we get a 4? You can't even get a 4 out of this. Huh. Well, I have lost the theorem, but if somebody can Google it, it's under longest increasing subsequence. It's a footnote there that maybe it's n. Even if it was n minus 1, I still don't have the theorem. But anyhow, it's a footnote. What the theorem, how the theorem goes. And unfortunately, I don't. I can't take the time. But if somebody Googles it,
Well, if it is n minus 1, then we have it.
Yeah, maybe it's n minus 1, but I'm not sure that this. I recall. Hold on a second. Okay, I'll get fired for this, but I want to know.
I found the theorem.
Great, it's Whittem, right?
Any sequence of n squared plus 1 distinct integers has an increasing or decreasing subsequence of length n plus 1.
So n squared plus 1.
Yeah, n squared plus 1 has an increasing or decreasing subsequent sequence of length n plus 1.
Well, how big was this one that we have? It's 8, right? So I would need I need 2 more, right?
Go to 10, or you could go back to 5.
10, yeah, I'll go to 10. So 5, 9, or something like this. Okay, so this is 10 now, because n is 3, so we can find a 4. Yeah, I'm sure I can get a 4 out of this. 2, yeah. I get a 5. Let's say 2, 3, 4, 5, 9. So I get a 5. So yeah, it's that's not as impressive. But of course, the question becomes, how did they get this, and why is it so famous? But that's a different issue. Okay, so some of you guys are interested in programming, and the challenge is to find a linear time algorithm to get that longest increasing subsequence. And I'm telling you, this is like an alien kind of thought process, and it doesn't do well with the human brain. At least my brain, it doesn't do well with it. And I don't know if it works, if that's a problem with other people. But it's quite interesting, and the time is not linear, but it's close to linear. This is the time you can get. The technique is called dynamic programming. It's very interesting. Sorry to take so much time on this, but I'm just telling you, this is the essence of the issues that come up when you're programming. And if you do this problem, if you spend the time, you'll learn gobs about programming, just gobs, just all sorts of take. It has a binary search in it. It has updating arrays, and a very, very creative approach. It is very creative. Okay. Just Google longest increasing subsequence, and you'll get a link to it. Anytime you spend trying to program this without looking it up, it'll. What do they say? Cast your bread. How does it go? Cast your bread upon the waters, for you'll find it after many days, or something. I forget how it goes. That's exactly it. Was it Tracy Whittem? I think it's that, or no, actually Erdős. This is a theorem of Erdős. Tracy Whittem is doing something similar, but it involves something about the largest eigenvalue of a matrix. I don't know, something related. All right. Okay. So let's see if I can continue to make a fool of myself. Thank you guys for putting up with that. But it's my belief that this encapsulates the essence of programming, the essence. So let me try to see if I can not make a fool of myself. The next thing is, there was a hole in what I gave you. We were looking at, I think, problem. So this was this, and we did it, but I don't know how well we did it. And y was e to the x, and the problem was to find the expectation of y. Forgive me for reviewing this, but if you're using the theorem, I think it's prop 2.1, you simply, what do? If using that proposition, I think you just do it by this. The E is that function times the distribution, the density of X, which is just going to be 1 here. And very quickly, so this is
Okay, so where I'm losing you, Professor, is like the density function. Is the density function the uniform distribution?
Yes.
Okay.
Yeah. So it's just a pop-up. So 0 to 1. So it's 1 there and it's 0 off.
Right. Yeah. The function for the uniform is f of x equals 1. It's just from 0 to 1.
The density function.
Sorry. Thank you. Thank you for, yeah, the density function is just 1.
Yes. Yes.
Okay.
Right. Now it could be careful now, because when we did this, we did it from alpha to beta, right? Or beta. We looked at different. This was alpha, this was beta, and then we had a pop-up here. But you see, that pop-up won't be the same height as 1 necessarily. It depends on alpha and beta, right? So we have to go, the height has to be 1 over
beta minus alpha.
Yeah, so we have to be careful.
Right. In this case, it's 1.
Yes, right. They're trying to make everything simple, and they fooled themselves, because it fooled me too. So let's just check this. So this is a theorem that this is the way you do expectations. You put the function of the variable here. I mean, this is the theorem that applies to this. But you see, that's not the definition of expectation, right? I mean, it would be if y is that, you need to, going back to the definition, what would it have to be? Minus infinity to infinity, y times f of y. Okay, this is the definition of there's no like function of y here. This is the definition of expectation. Okay, so what the book wants us to do is to struggle with by elementary means to get to what? To get to this answer. And I'll try it again. Okay. But so they're saying this example, it comes before Prop 2.1. And what was the technique? Well, okay, maybe I should, tell you that if you're doing it by definition, what you need is this creature right here. So how do you get that creature? How do you get that density? Does anybody want to suggest a way to do this? I mean, you want this density, so how do you get a density?
Taking the derivative of the CDF?
Yes, that's the technique. And it seems like too much to do about nothing, right? But I swear to you, when I taught the course the time before, we used a different book. And this is craziness, but like 25% of the first 100 pages was making these change of variables. It's like they were addicted to it. And they just want it over and over and over again. And they do it like 3 different ways and stuff like that. Well, here you got 2 different ways. Either use the proposition or you do it by hand. So it must be that statisticians find this critical, but I don't know enough statistics to tell you why. So we know what the answer is supposed to be. We need that guy. So how do we do this? I mean, by what means do we get that? I guess you take the cumulative distribution function. What does that mean? This is probably that y, which is e to the x, is less than or equal to. So less than or equal to x. Maybe I should have used a different variable here. Okay, so I do that. So this is is what? This is the probability that x is less than or equal to log y. And so,
Real quick though, just because this is something that I've struggled with from 341, can you just help me out with the change of variables here? So we have e to the x is less than y, and
okay, you just take the
yeah.
log to base e of both sides.
Okay. So we're basically solving for x effectively.
Well, you want to do that because now you're
now we have x, which we know the distribution for.
Right, and it's actually a simple distribution. So we can do what? I mean, it's an integral from what to what? Well, you want to go from 0 to log y of that distribution, right? Yes. Okay, but the distribution is just 1. So it's going to be 1, and you integrate that, you get an x, so it's log y. But the y's, it's important to realize that the y's go between 0 and e in this formula. So when it comes to taking the derivative,
and the reason it goes from 0 to e is because x goes from 0 to 1.
I'm sorry, I don't know why I did that. I'm sorry.
Okay.
Sorry, just because what? Look at why.
Okay, from 1 to e. Yeah, so we get that from substituting.
Right. It's important that you've got a function here. Where is it applicable? You know, that's something that should be noted. So now let's go back to this definition down here. So this the range, the space of y is 1 to e. So you're gonna go from 1 to e here. However, you know something about this. Okay, this is the definition. This is the definition of the expectation of y. This guy is what? We've calculated because we took the derivative here. This guy is what? Is 1 over y. So now I've got myself into a problem here with space, but y times 1 over y is 1. So we're going by the definition here. So that would be what? So I don't. So this is 1 over y. So what is this whole thing equal to? From 1 to e of 1 is what? It's e minus 1, which is what we got using the theorem. Okay. It's awfully quiet now. Maybe we just, this is.
No, it's more, this is stuff that, this is something that I did in 341 as well, but I really struggled with it. There's just a lot of steps, and I think I get it along the way, but then I make a mistake somewhere. So I'm just, I'm trying to do it on my own paper and write down exactly what's happening each time. So I'm not missing anything.
My feeling would be to use the theorem, use the proposition.
Well, yeah, sure, absolutely.
Yeah. Don't kill yourself
with changing variables.
Yeah, because when you look at the proof of the theorem, it's non-trivial, and they're taking into account all that stuff. So I don't think reinventing the wheel. The only reason I did this is because there's a problem in the back, 5.40, where they ask you to do this again. They ask you for this. And it's why would they do that? I don't know. I guess they feel it's important to at least get the beginning of this, Okay, can I go to something else? But maybe after the class is over, we could talk about this some more.
Well, I got it. I needed to.
Okay.
The reason I was quiet was because I was writing a lot.
Yeah.
But yeah.
So let's see. So something that I haven't done because it's very icky to do, and it's absolutely my worst point. where at least a strong suit is this translation of a normal curve into the unit normal. Okay, and we didn't really do that, but it's sort of interesting. It actually uses the fundamental theorem of calculus too to be able to do that. It's amazing, you know, that require that. Well, let's see. So what is the goal here? The goal is this. The goal is not to write in the washout. So if x is normal, mu, and variance sigma squared, then x minus, let's just do it carefully here. Let's give a name to this translated. So if you have y equals x minus mu over sigma, then y is normal 0, 1. I don't know that I did that, but it's just like I don't think I did it because I need something to do this. It's a little bit technical here because we're dealing with an ugly density function. So what do I need to do this? I need a little lemma. So x is what it is, and I'm going to look at ax plus b, and let's see if I can do this. So this is what now would the mean be? Well, look, I mean the mean of this is whatever it is, and you're multiplying everything. You're scaling up by a, so it's going to move it over by a, but then you know, so it'll be a times this, but then it's a scale here, but then there's a hard translation to the right. So you used to have mean mu, but now it's a mu plus b for the new mean. And then let's see if I can remember the variance is that. So how to do this? This is tricky. How do we set this up? I guess we use. Hold on a second. Let's do the CDF trick again. So let's use f of y. So let's let y equal ax plus b, and let's try to get what is this a sort of indirect way to get at this? But when we get the CDF, when we hit it with the derivative, we'll be able to see if the density function is obeying this conclusion. Okay, we'll be able to do that. But right now, let's just take the density function of y. So let me. So that's the probability. The probability that y is less than or equal to x. That's the same as the probability that ax plus b is less than or equal to x. Okay, so let's fiddle with that. So this is, now we can rephrase this back into the normal density, so we can, into expression involving the normal density, so the regular one. So, the normal, just x. So what is that? So if I'm solving ax plus b is less than or equal to x, that's the same as saying x. That's the same as saying the probability of x is less than or equal to x minus b over a. Now you have some choices on what you're going to do now, because remember what's the goal here? I'm going to be looking for the density function of y. So I'm going to be taking a derivative at some point. Okay, and I'm going to see if indeed the two parameters are these right here. So what is this? Now I'm deviating from the book here. So I'd like to know what this is. That's minus infinity to x minus b over a of 1 over square root 2 pi sigma e to the minus x minus mu squared over 2 sigma squared. Okay, dx. Now, again, what I wanted to get was this derivative. So this was f y of x, but I really want to take the derivative. So when I take the derivative, so that means that, so f of y of x is what? Now I've got to know my calculus or remember it. It's been a long time since I taught calculus. But I have to take the derivative of this function and then evaluate this at that place. So the derivative is what? It's 1 over a. Just make sure I'm on track here. I'm not following the book, sorry. 1 over a, and now I have to do what? 1 over square root 2 pi sigma. And now I have to express this. Let's express this guy right here. So this is e. X, I have to put this in for x. So e to the minus x minus b over a minus mu squared. X minus mu down. X minus mu squared over 2 sigma squared. I'm sorry, it's just very hard to write this with the restrictions I have in terms of space. Okay, so everything is here, even though it looks crowded, you know. So.
Right. And so, just to clarify, where's the 1 over a coming from? I mean, I'm assuming it's.
Oh, it's the derivative of this.
Okay, thank you.
If you see, when you take the derivative of the whole thing, you've got to take the derivative of this times this evaluated at that point.
Okay, thank you.
But, I mean, it'd be fun to prove the fundamental theorem.
It's fine. I'm
It
good.
would be fun to remember how to do it. Okay, so, but supposedly, what I'm shooting for is that what I have in hand here is exactly this. So let's check to see if that's true. So, it has to all happen in a foot here of space. So you definitely have 1 over square root 2 pi. And then you see you have an a times sigma here. Okay, a sigma. So that's functioning. Let me use a different color. That's functioning as the variable sigma. That's the parameter sigma. So that's the parameter sigma. Now the rest of it now comes, to do this in my head is a little difficult, but minus, okay, so now you have to do this as x minus something. Notice, this will be x minus b plus a mu, x minus b plus a mu squared. And then the thing that comes below, you see there's an a squared here, but I'm going to let that a squared drop below the division line here. So that would be 2a sigma squared. So this here, that makes sense. So you normally have a sigma squared. So this is the same thing that we have over here. And what's the new mean? So this is the density for a normal random variable with mean b plus a mu and variance a sigma squared. Okay, so that I don't know, it's hard to see, but I'm sorry, guys, it's the best I could do. But it does work out. So what's the conclusion? So this if x is normal with mean mu and standard deviation sigma, then ax plus b is normal with these parameters. Okay, I'll look at the chat here. I'm sorry about the space, the font size. There's nothing I could do to. I did this a little bit differently. They didn't have to write this out, but I don't know. Just this is the way I feel comfortable doing it. Okay, so assuming that you believe this now, believe this result, then how do we get this result right here? So let's think about this. So if we look at y, I don't know where to put this. I don't want to erase something in case somebody asks a question. I think I can erase this. This was the start of the proof that was easy. What is going to be A and what is going to be B? So let's figure this out. So A, so the y I want to use is this one right here. So A will be 1 over sigma. And the B is what? The B is minus mu over sigma. I don't know if I'm writing too small for you guys to see, but that's the A and the B that we want to use if we're going to investigate what happens when we normalize this random variable x in this way. So let's use the theorem that's right above to figure out what the effect of this is. So this will be normal with what? What does it say? It says it'll be normal with A mu. So A mu, A is 1 over sigma times mu, and then you add the B, which is minus mu over sigma. So what is that quantity? Mu over sigma minus mu over sigma is 0. And then what about the standard deviation? The standard deviation will be sigma times A squared. So sigma came before, but what is A here? A is 1 over sigma. What is that equal to? That's 1. Okay, that was the simple part. I mean, but I guess the hard part was to crunch through this. So this explains why you take x minus the mean over the standard deviation, not the variance, okay? It's x minus mu over sigma. That gives you a standard normal random variable. So the mean is 0, the standard deviation is 1.
So just to kind of follow along what we have here. Mm-hmm. So the work you have in red at the bottom,
yes,
shows what you have at the top, that if you have a random variable that you translate and you dilate ax plus b,
yes,
the normal does that. The mean becomes that, and this variation becomes that.
Exactly.
So when we cleverly choose
right.
Yeah, our A and our B, so that it becomes 0, 1 because of what we just showed there.
Exactly. And
okay.
What I'm saying is it's not obvious, because a lot of people might say, why don't we divide by the variance? It makes sense, right? But that doesn't give you the standard normal. It's always x minus mu quantity divided by sigma. You've got to do this. And with your data, you do some experiment, you collect data, which you suspect is normally distributed. You normalize all those, they call them scores, all of those data points, records get normalized. So that you look at it, now you know, is that what you're looking at, is it unusual, or could it just be explained by chance? That's the what is that? The essence of Bayesian statistics? I don't know. Unfortunately, there's a move to get rid of it. No more t-tests. That's what my statistician friends tell me. There's been a couple of Scientific American articles on p-value, and they say it's unreliable. Sometimes that you get a p-value which says that there's significance, but you know darn well there's no significance. So in science, they're questioning this stuff that's been going on for 100 years. 100 is exaggeration. I mean, statistics got started when? The 40s, after the war. Okay. What's the story about this? It's the real story. Japan was devastated in World War II. They had to re-industrialize, and they were putting out products that were inferior. I remember in my own life experience. My sister got an old Toyota something Corolla or something, and it died after a week. It was used, of course, and their product. But then what they did is they imported a statistician from the United States, and everything changed over there. All the QA QC people, they just went to work, and the products became the equal of the United States, and now, in my own opinion, it's superior.
Yeah, like Japanese cars are the only cars to get.
Oh, I don't know. I don't want to be that. I mean, I could get arrested for saying something like that. You know, I mean, I mean, if you want to go by popularity,
And
I think
also
the Ford
Japanese audio
pickup is the most.
capacitors.
Yeah, the way I am, I always think of reliability because, car repairs just can kill you. Just absolutely, especially if it's a foreign part, right? If it's a German part, it just kill you. So anyhow, yes.
I can tell you in the music business, Yamaha musical instruments, whenever they first were being made, they were not very good. And it had nothing to do with like quality of the stuff. It just
yes.
They just couldn't figure it out. But then they disappeared for a couple years. And what happened was they got instrument makers from Europe to come and show them how to do it, and they figured out a way to make them. And now, honestly, I absolutely love them. So I prefer them over like a Mizell or something like that. So whenever I have a student who is starting, I'm like, if you can afford a Yamaha instrument, those are the best ones to start on.
To start,
very easy to play.
When I grew up, my dad had a Steinway, but it was a upright. But oh my gosh, it had a brilliant tone to it. Which Yamaha, obviously, they're not gonna. But the price difference is just astounding. A top of the line Yamaha versus Steinways. I mean, it's a factor of 4 or something. It's crazy, the difference. It's just crazy. But and it depends on the music you're playing. Sometimes you don't want that brilliance. You're playing something from the like Bach or something like this, and you don't need to overpower. That wasn't the way he envisioned it. He doesn't hear it that way. Okay, where was I here? I'm sorry. I just wanted to tell you that story about
going off track.
But it's important to know that statistics made a huge difference in Japan's ascendance. Economically, a huge difference, and there was one guy that started it that went over there. Okay, so what am I supposed to do next? So if somebody tells you statistics is meaningless or pointless or numbers can lie, just look at the powerhouse. The third largest economy in the world, Japan?
I don't think that anyone is really saying statistics is worthless. There's so many jobs in statistics.
Well, some people sometimes say the numbers can be.
That numbers can lie and stuff like that.
They can be presented in you can. Like the case of smoking, right? The tobacco industry held off the scientists for years and years and years and years, saying, "How do you know that smoking causes cancer? Okay, how do you know that it? It's just definitely a correlation. Nobody's doubting that." And those stupid lawyers on the I don't know if the judge was stupid or what, but the argument that the tobacco company was putting was that it's not the tobacco that kills you. It's the susceptibility you have. You have something about you need to smoke. That's the problem. You have some biological need to smoke, and that's what kills you because you're susceptible to wanting to smoke. I mean, it's just crazy. But they got it so that it wasn't the killer dagger. It was the some weakness in your mind, and they actually sold it on the judges for 20 years. Okay, did we do the how far did we get on the information transfer problem? Did we do that whole thing or not? We started talking about it. Was it familiar or not? Or,
it doesn't sound familiar.
Oh, example 4E, very interesting here. Okay, this has to do with noise and channels sending information. for those that aren't,
Yeah, we literally finished up with just introducing the problem.
got it.
I don't even know if I even wrote it down. It was right at the end.
Let's try to make this really simple. We get it, but not too crowded. If things get set binary, right, 0 or 1, usually that's the way. But if it's a particularly noisy channel, you might want to send -2 in place of 0 and +2 in place of 1. There's more separation maybe when they get received. So this is the message. By the way, just in general, you understand that there's no transmission of anything without the potential for error, right? I mean, noise and stuff. And somebody says, "Well, we have a computer program, and the computer doesn't make any mistakes, does it?" Does it? I think I've heard that computers do make mistakes. It's just extremely rare. Okay, but it does happen, and for that reason, you have to have certain programming languages when you're trying to prove something that have tremendous redundancy. So it is impossible to make a mistake. But noise and errors creep into everything that's transmitted. And I say, no, a computer is transmitting things from the CPU to the memory, and things are moving around. So if the message in a bottle, the message is 0, what are we going to send? -2. If the message is 1, we will send +2. But the question is, what will be received? How do we take into account the noise? Now, this is the beauty of the normal distribution. It's so good at modeling noise. Okay, it's eerie. So what's received? Received here will be -2 plus this standard normal, or here it would be 2 plus the standard normal. And the question is, how are they getting interpreted? So this is interpreted.
When you say standard normal, we're saying that the variance is 1 for sure?
Yeah. Variance is 1. So it looks like, okay, how to make a picture of this? Suppose you have 2 plus normal, right? What would that look like? Well, it'll be a standard normal, but everything's moved over by 2. So the center would be 2.
Variance, okay, great.
What are you looking for? You're looking for a 2, but because of this noise, you could be a little below or a little above, with the probability. It's just it's a spectacular model for noise, okay? Where was I? Okay, so interpret, how do we interpret? So the problem goes like this. So interpret. So if R, if what R is greater than equal to 0.5, then we're going to conclude. So there's a lot of pieces to this. I just want to get everything in there. I don't want to totally, blow it worse than I've already have. Conclusion. This is what you conclude, that the message was the original message was 1, which is an error, and if R is less than is less than 0.5, then we're going to conclude was 0. So what do we have to compute here? I forgot what the problem was. What's the probability of an error? Given that the original message was, there's 2 possibilities there. So what is you want to compute probability of error given that a 0 was sent. Of course, that's the critical thing, and it might be in a washout. 0 was sent. Okay, so now it's time for another color here. So now we know what we want to do. So, and also, of course, we want to do the other one, the probability of an error given that a 1 was sent. So So what?
I think I understand what you mean now, or what you meant a long time ago when you said that a random variable is rather a misnomer. It's more like a random function.
Yeah. There's no. It's not a variable. It's a function.
Yeah,
It's a
that's
function.
funny.
It's just old. There's a lot of things. Some words in mathematics are used in so many different contexts to mean so many
That's
different
what I
things.
hate about it.
The word complete. Sometimes paradoxically, mean one thing in one context, a totally different thing in another.
Yeah, I like being more consistent.
Well, you can't because the language. We run out of terms. Okay, so how do we calculate this? So if R is what you received. So okay, let's be looking at this one right here. So what does that mean? R, so that's -2 plus n is greater than or equal to 0.5. That's equivalent to what? That's n is greater than or equal to 2.5.
And yeah,
Right? So we could do this with our table, I mean, we could figure out what this is. So n is greater than or equal to 2.5. Let's say, how about I let's draw a picture first. So here's the standard normal. So it's not going to be a very large probability. But how do we calculate that? And what exactly am I calculating? I'm calculating this dust in the tail here. The blue dust. How do we do that? So to get the blue dust, you want to review that with the table? How do we do that? So it's 1 minus, so this is 1 minus phi, which is the CDF of the standard normal of 2.5. You understand? Everything is everything, but we just want the little blue. So I'm going to take everything which is 1 minus all of this. This is the CDF up to 2.5. I don't know what that is. 2.5 is
0.62%.
0. So this is very, so 1 minus 0.62.
Percent. So 0.0062.
And it doesn't look right. Oh, the answer.
Yeah, sorry, I should have been here.
Sorry, you threw me for a loop. Okay, that's like I was thinking that's pretty high there. This is not a good setup. Okay, so the answer is 0.0062.
Yeah.
So thank you very much. Okay, so this is a low. There's been some precautions here so that things aren't. This is built so that we won't get too long. What's the other one down here? So that this one here would be 2 plus n less than 0.5, and you make an error if when n is less than minus 1.5, right? It's a little bit different. So how are we going to do that one? Well, this is -1, and this is minus 1.5. That looks like just phi of no, okay. Now, how are we going to do it? So how are we going to do this? So you go 1 minus phi of 1.5. So 1. I'm sorry, it's awfully messy here. It's awfully messy. So you go to 1.5. Okay, so I want less than, so I'll take 1 minus phi of 1.5 will give me the tail on this side. So 1 minus 1 minus phi of what? Of 1.5. And that should give me this tail. It gives me this, but it's symmetrical. And what is this number? Is there a calculator?
The whole thing is 0 point, let me make sure that I do this right. It's 6.68%, so 0.0668.
6.68.
0.0668.
Well, this is higher.
It is.
0.068. This is higher.
What did you get?
But that's
for-
not what I said.
What is that?
I said 0.0668.
Oh, 0.668. Okay, sorry. That still is order of magnitude larger than the other one. So I'm trying to figure out.
It's not a surprise because it's 1.5 standard deviations, for the other one is 2.5 standard deviations.
Yeah. Yes. It's not symmetrical. I don't know why it wouldn't be. I don't know why this asymmetry is. I mean, usually when the guy like Ross does a problem, there's a reason, why he chooses the numbers he chooses. And I don't know anything. I don't know enough about information, theory, whatever, to tell you why they don't just do it symmetrically.
I kind of wasn't paying attention while I was trying to figure out how to calculate the CDF, but like on my computer, and I figured it out. So now, what's asymmetrical? What did we find?
Okay, so
how come it's? Why is it 1.5 versus 2.5? I don't get that.
Well, the error in this one, in this scenario, is this little blue thing right here, right?
Mm-hmm.
The error, the possibility of error in the other scenario is this, which is more. I mean, if I drew
I see now.
I'm not saying it's 10 times more, but apparently, it looks from the picture possible that it looks, like it's off by the other one. The other one was 0.006. This is 0.07.
Okay. I see. That's because our interpretation function is kind of weird.
Yeah, it's not symmetrical, and I don't know why. I should know this, and maybe it's so obvious. It's just.
I can see it now. So it's like the message is either 0 or 1. But what it's sending,
either -2. The message is either -2.
Well, that's the. Yeah, but
so
like,
where's your dividing point? So 0 would be the dividing point, right?
What I'm saying is, the interpretation is like using one nomenclature, and what's being sent is using a completely different one. So what's being sent has a mean of 0, like between the two values, but the interpretation is expecting the mean to be 0.5.
Right,
so
right.
That's why
So
it's
if
weird.
you're here. If you're here, you're saying that the message was 1. If you're here or above, and if you're below, you're saying the message was 0. So it's biased. You're
it errs on the side of -2.
Yeah. So there's not. Maybe he did it on purpose just to confuse the teachers. No, I'm kidding.
Seems like it.
I have a feeling it's because if there's an error with sending a 0, there's more problems. So I guess. So.
Oh, that's a good point. Wait a second.
Want
This
to
is a good
send a
point.
1 when
Because if you knew if there was a predominance of 0s or 1s, you would want to err on the side of what I mean. If you knew that there were 10 times more 0s than 1s, maybe that would change this.
Yeah, or maybe if the 1 was like really critical to, like, if you didn't send a 1, you really don't want to send a 1. Something like that.
If you mean to send a 0, more problems are created when you accidentally send a 1.
Yes.
Is my guess.
Idea.
I know. Like if you put a bunch of 0s, that's usually what's there whenever you end a program.
The background noise. It's like or not noise, but it's just the template, right? The template.
Yeah.
The template. You can't. When you think about it, though, I mean, I may be off the wall here, but if you're sending numbers and you have a lot of surplus of 1s, you can get out of control really fast, right? If they're the, what I mean, the first 1 stands for how many 2 to the 10ths you have. The next one is 2 to the 9ths. You know what I mean? But if you have 0s, it keeps. You're not going to get too many 0s. Will keep your numbers under control. You're not going to overflow by mistake. But having said that, I wonder if that's even true. So which one is This is if it's bigger. Yeah, it's. Oh, whatever. Okay, I'm too tired.
Yeah, no, the error when sending a 0 is much lower than the error when sending a 1. You have a greater chance of a 1 accidentally being sent as a 0 than a 0 accidentally being sent as a 1.
Then what I said is bogus because I'm thinking of control. I think the ones would count more than the zeros because you could sending numbers, right? And the numbers could get way out of range. Right, so you're saying which one is the bias? I mean, it's this error.
You'll tend to get more zeros.
Yeah, it's biased towards zeros.
Hmm.
But that's what we were saying.
That's what we want. Okay. Why am I
It's
so
biased against ones towards zero.
Well, here's the dividing line, right?
Yeah.
So if it goes up here,
If it goes up there, then we interpret that as a 1.
it's a 1.
Yeah.
So yeah, it's gonna say 0 more frequently.
Yeah.
Well, like I say, if overflow is a problem, maybe it's good to keep the numbers under control. I don't know. All right, what's the next? The next thing is the famous memoryless thing. So what's this example of a memoryless random variable? So what is it?
Oh, the exponential.
Yeah. And what is its what? So it's what is it? It's e to the minus lambda x. So probability of x equals. So x is let's say x is an exponential random variable in the washout. No. So what is its density? So f of x equals lambda e to the minus lambda x, and this is for x greater than equal to 0 and 0 else. Okay. And what is the? Okay, first of all, if you integrate this density, you get 1. Let's not. I don't want to bother with that, but I would like to know f of u. I'd like to know this, so I don't have to keep on doing this for the examples. So how do I do? So this is the CDF of x. So how do I calculate that? From 0 to u, lambda e to the minus lambda x dx, and this is what? This is minus e to the minus lambda x from 0 to u. So it's going to be, what is it going to be? It's minus e to the minus lambda u plus, now if I evaluate it 0, that's 1. So 1 minus e to the minus lambda u. Lambda u, sorry.
But that's not negative 1?
No. Why would you think it was negative 1? So, okay, so the antiderivative of this would be this, right? Right, because when I take the derivative of that, I get this.
Yeah.
So if I evaluate u and I get minus e to the minus lambda u, then minus is 0. So it's 0, it's e to the 0, which is 1. But there's a minus sign here. So are you okay?
No.
Which step are you?
I don't know. I must have forgotten everything about math.
No, because this is not it. We're not doing parts or nothing like that. So you just want to find an antiderivative for this, right? So what has this derivative? So this is the derivative you want, right? What has that derivative? This is the derivative of something.
Right.
Well,
So I think I get that because it's like the
Well-
derivative of e to the ax. Just a can be any arbitrary.
right. But this is a
So-
little bit different, right? Because you're going to have a minus. When you take the
It's a
derivative of this, you get a minus that you don't have. So that's why you have to put a minus sign in there.
Okay, so I get that, but then when you're evaluating it
From
at
0 to u.
0, I'm not.
Oh, you do
understanding.
you do the upper one first. So you do it
Okay.
x equals u
Well,
first.
for you, I see you just plugged it in, but then I don't understand. Like, isn't e to the power? Isn't it negative e to the power of 0? So then, shouldn't that be a negative one?
No, okay, let's do it step by step. You put in the u first, right? And what do you get? You get minus e to the minus lambda u, right? You good with that? If you put in the u. Now you subtract off minus e to the 0, right?
Wait. Okay, so it is -1. Okay.
No, there's two
We were
minus.
Yeah,
subtracting
so
the
yeah,
minus
minus
one.
-1.
Okay. That's
So
what I
it's
was
1
missing.
minus e to the minus lambda.
Okay. Thank you. That makes sense.
Okay, none of what I'm doing here gets us any closer to proving this weird memoryless property. Okay. So what is this? What does it mean for something? Yeah.
I was gonna ask, like, I want to see if I know the definition of memoryless. Is it like the probability of x plus b, given that x is greater than b?
Hold on, let me write it down.
Okay.
X,
I want to just see if this definition is right. X plus b, so something. Like the probability that x is further than a certain amount, right?
oh, greater than, not equal, but greater than b.
Oh yeah, sorry. Yeah, x is greater than b. Oh darn.
Okay, let's do this. Let's draw a picture. So suppose this is S, and this is S plus T. I'm only drawing that because S comes before T in the alphabet. So the probability that X is greater than S plus T, given that X is greater than S. You see, so you were saying, what's the probability that it?
Right, yeah. X
Given
is
that it's
greater
already
than s
made-
plus t. Yeah.
Given that, okay, so what's the given? You've already got this, so probably, given that this is equal to the probability of what?
X is greater than t.
Does that make sense? Because you're saying you're here. What's the probability of it's bigger than it went farther than this? But that has no bearing on the fact that it, given they get here, it should be the same as just doing
I
t.
can't see. What are we looking at?
Sorry,
Oh.
sorry, I can't speak. I'm tongue-tied here. But okay, so this is this weird property. Okay, you're asking what's the probability that it's bigger than this, given that it's already bigger than this. Okay, but it's the same as it's as if you started at S. It's having already done S doesn't really matter. It's like you started at S. What's the probability of being greater than T?
Oh. Well, then wait. Does it work the other way around?
Maybe I should have written it.
That's confusing.
Uh,
What is S and T here?
T is just this. T is this. Is this the length of that interval right there?
Okay.
But maybe I could have written this. Hold on. I could have. I think the book has them reversed, the S and the T. But it doesn't. It shouldn't matter.
Yeah. It works the other way around then.
It shouldn't matter. I mean, it's symmetrical. If I put T and T plus S here, shouldn't matter. It's the idea that you're going another T. That you're here. You've already done the T. That has no effect on the probability that you're going to go another T. From here. I mean, that probability is unaffected by the fact that you've
This
already.
doesn't hold true for every kind of function, right?
Well, it doesn't hold true in real life. It doesn't usually. There's a
'Cause
Right,
I
but the
can't
point is,
conceptualize this. I don't
yeah,
understand what it's saying.
this property is called being memoryless. So not every function is memoryless. We're trying to show that the exponential is memoryless.
I think this
Okay.
most.
So what does it mean?
Okay,
What
look,
is
look,
this?
look, look. Our intuition
What does it
is
mean?
if you keep bending a strip of aluminum, you would get what do you call it, case hardening or something like that. You have this it's something starts with E. It's some sort
Yeah,
of
I see
effect
what
you get.
mean.
And in fact, so it's definitely remembering that it had a lot of flexes there and it's going to break. So it's
Right,
it's
right.
very anti-intuitive for us to think that probably a break in the next 5 minutes is independent in some sense of what happened all the time before. Because before, if you're doing this, it's accumulating strain and it changes the crystal structure and it breaks. So this is a really rare. I mean, it's not rare, but it's a very odd. From the physical standpoint, physical science, it's very weird. It's like radioactive decay thing. Like an atom may not have decayed for 4 billion years, but the chance of it decaying in the next 4 minutes is probably even doing the next 4 minutes is independent of the fact that it hung in there for 4 billion years. I mean, that's really weird. That's weird, right? It's like it doesn't, there's not, things don't build up, they just don't.
That's really so. What you just said there kind of makes it make more sense. Like I can understand it better now because I know, I know what that means. So that's really cool. So it's like when things are completely independent, then so like
Well, I don't know if independence is the wrong.
Because logarithmic decay or exponential decay or whatever you want to call it is that's what happens with things that are generally independent of stuff like that, where it's just completely random.
Okay. I mean, this is
so that actually now it kind of makes sense to me.
But I'm not a statistician, so I could, I can't tell you how this has a lot of uses, and I'm thinking in lifetime situations, like the lifetime of a light bulb or something. Sometimes it doesn't matter how long it's been used. I mean, it's just the way that these things are produced, or the physics of it are weird stuff. You might have a light bulb that lasts 20 times longer than the normal, amount. It's very it's uncertain when it's going to go out.
So
you can't say, well, we used it for 10 years intermittently, and now it's ready to go. No, it's not kind of like that. I guess it has something to do with light bulbs.
Light bulbs,
old school light bulbs. Okay, so but getting back to what Abe was saying, let's see if indeed the exponential has this property. Okay, there's no. How do we? And what exactly? How do we rewrite this to help ourselves? So let's rewrite this. So if and only if what? What's the definition of conditional probability? So this is the probability of what? X is greater than S plus T.
Oh, I think I understand it from a math point of view now too. It took me a while.
And then probability of X greater than S. Okay, so this is an and here, and I never wrote an and that way. Okay, but just beware. This is what the book does. And then, so that is what? So this is equal to P of X greater than T. So I'm just reinterpreting. This is what we get from what we expect to have happen. Let's see if it really happens with the exponential. So this probably that it's greater than S plus T and it's greater than S. What's the same as probably it's greater than S plus T? And over what? Okay, and then I'm going to multiply this over here. So the probability of X greater than S, I'm going to multiply this times probability of X greater than T. Okay, sorry, it's messy. Okay, so is that, these are all equivalent. So is this true for the exponential? Well, I don't know. We have to use this formula we have down here, I think. See, it's in red, white, and blue. Now, the formula says what? So the probability that X is greater than S plus T would be 1 minus the the CDF of X plus T, right? But 1 minus gives me E, using the formula, and everything's, so this would give me E minus, E minus what? S plus T. And let's just check this. Is that equal to, remember, I'm using this formula here because I'm taking, is everybody clear? I want, this is up to that, from 0 up to that, to U, but I want greater than U. So I have to go 1 minus that. And that clears out the 1, and it takes the minus sign away from the exponential. So e to the minus s would be the, I forgot the lambda, I'm sorry. Okay, back up. I'm taking lambda equal 1. Okay, let's do it again. So this would be e to the minus lambda s plus t. And the question is that equal to e to the minus lambda s times e to the minus lambda t? And that's a property of the exponential function. I guess that's what Ethan was saying. Exponential decay, or a growth. I mean, it's a decay situation, but this is the.
Can you explain
It's
one
true.
more time why we don't write the 1 minus?
Yes. Okay. This is a simple thing. This is the CDF. So
Okay.
if you have the, I don't know if you can see over here this small thing, but you have something like that, right?
Right.
So if this is U, what you're doing is you are accumulating this area here.
Yes.
However, what they're asking for here is greater than. So what they're asking
Oh, okay,
for the
gotcha.
red, so we'll take 1 minus
Yeah, now I see.
the blue. So the blue is this.
Mhm.
Yeah, and that will kill that. Yeah.
Thank you.
I don't know. You know what? I think I have tried to go to the Wikipedia to get a deeper understanding of the memory list thing, and I hate to say use bad language, but I get absolutely nothing. It's like what I get is basically what I just put on the board, and it's sort of my feeling is that this is completely unintuitive, and you just have to. Just from experience, we realize this models things, very well, and it just can't.
Yeah, that's
can't
why.
get-
I mean, even though I've been through several physics classes and they talk about this stuff with atoms and nuclear decay and everything. I still had to take a few minutes to just internalize it and think about it.
Yeah, I mean, it makes you wonder what kind of world has this property. And I guess we were talking about the quantum world, right? We're not talking about the macro world, because I don't believe that. Well, I guess if you read our book, they say models earthquakes and da da da, like that, and stuff like that. But for this to be an exact model of physical behavior, that's very strange to our concept of reality. It's just not. Our mind is good at certain things, right? And that's from evolution or whatever. We're good at like processing visual information. In fact, our processing of oral, auditory stuff is unbelievably fast compared to visual. I mean, it's really, really something. I mean, it's amazing. But something like this, it's like how to say, it's like a resetting, right? You want to know if this atom is going to decay in the next 5 minutes, and it's completely irrelevant what happened prior to our starting the observation.
Yeah.
Most things have
there's
history.
a lot of things that I would say that if you go looking for it, there's a lot of things that you could find in a macroscopic sense that I think especially in gambling and stuff, but that you could use to sort of model this. But yeah, it's not something that you see as often as you see in the quantum world, I'd say.
Well, I guess we always talk about, at least my statistician buddies, colleagues say, well, it's lifetime distribution, lifetime, and you can think about that. If somebody's 98 years old, their probability of dying in the next year may be about the same as it was when they were 89 years old. I mean, I'm just thinking of this, because it's a random thing that causes you to. I mean, this is what I've been told. It's a kind of a. Maybe I shouldn't use death in humans. I should think of what kills a car. You know, a fatal thing like a head gasket blows or something. A fatal thing where you're not going to fix it. That car's dead. You know, and that's the sort of thing that's. You know, when you get to be a certain age of the vehicle, it could happen. It may not happen, or it could happen. You know, but it doesn't. It's not so much the exact age and how long it's been going without this problem. It's not. It's may not be an issue. You know, may not be a factor. So maybe, in some sense, all lifetime distributions. You know, when they're modeling lifetime situations of light bulbs, transistors, people, and stuff, maybe they have this in some sense.
I'm thinking maybe it's like a bunch of memoryless, like a good way to model like the car situation. Maybe like a bunch of situations like this where it's like equally likely to fail at any time, but because there's lots of different systems at play, the further along you go, the more likely it is that like it's gonna fail eventually. Like I don't know.
I guess I should stop.
Does that make any sense?
I've gone to the Wikipedia and I'm just very disappointed. It's just awful. And especially getting back to that.
Yeah, sometimes it does that.
Increasing subsequence thing, you know, that one, they go right to the code and they don't explain what they're doing, and they're all concerned about the boundary conditions so that this thing will run. But in doing that, they're like giving the finished product. They're not the idea. Now, Ames, a musician, a composer, I wonder, composers probably, they don't just come out with a finished product right instantly when they sit down. Maybe Liszt could do that. You know what I mean? You know, he was such a good improviser. But it seemed to me you have an idea of what you're going to do first, and then you realize, you know, hey, this is going to sound good, or it makes sense, and this is kind of neat. You don't just go to the sheet music and boom, you've got it. You know,
yeah.
This is my problem with the Wikipedia on coding. It's just like they go right to and then they're trying to. Well, here's how the algorithm works. You know, relative to their code, and they should try to just do it. I call it a human algorithm. Just what would.
Yeah, I totally agree.
In a reasonable case, what would you do to be faithful to this approach? And then you get the idea. Oh, now I get the idea of how it's fast. You know, why this is efficient. I get it. You know, otherwise you end up for some superficial reason getting the time. You know, counting loops or something like that. When's the next? Okay, that's okay. They've got a different kind of reality has set in. Okay, the next exam, as soon as I can. I'll put it together. What am I going to put?
One more exam and then a final?
Yeah. So I have to make this exam reasonable. It has to be reasonable in terms of length. But I will put in an ERP, you know, and I'll ask you guys to do it with a probability tree diagram and also theoretically. But I'll keep it down to like the one we had. I'll just do for 4 numbers, okay, or 4 letters, you know, whatever. Just for four. And because it seemed like it didn't do well on whenever it showed in the last exam. It didn't do well at all. And I'll have to put in some standard problems, from the book, but I'll change the numbers. So that means that the check people have to be on alert. They'll just say, "Well, this is funny. You know, there'll be a number change in there somewhere." High alert. You know, the check. You can tell them now to get their act together. At least I've done some discovery. You know, the latency is 20 minutes. I think I already told you. So they won't go longer than that. So if they can't crack it in 20 minutes, they just let it sit. It's good and it's bad, you know, because if you know they can do it in 20 minutes, you're probably not going to say, "Oh, it's take me 2 hours, 20 minutes." what's it going to be, you know? But yeah, there's some in the next chapter. There's actually some very nice problems, and we can get the essence of the next chapter in just a lecture or two. And then you're set to do the problem. There's nothing, you know, we use the joint, 2 uniform distributions joint. In that case, you're whatever. It's you can use geometry to calculate the probabilities. The thing I want to do on Thursday, I guess, is I'd like to start this next chapter and talk about the Buffon needle problem. It's an absolute classic, and you don't really appreciate the multivariable, the joint distributions unless you've seen that problem. Anybody heard of it? Buffon needle problem? Because they do it. I mean, it's like it's okay. I'm over the time. Hold on. Let me see. Yeah, as usual, I'm killing it on the time. I'm sorry, but I get back to your question on the exam. Yeah, I've got to put something together, but make it reasonable, not with the same time load as the last one. There definitely won't be any more. What was that? The expectation. Recurrence is involving expectations, and that's it. That's it. I don't even think I'll put that on the final. It's done. You did it. It can be done. But like I say, the problems in chapter 5, not good, not interesting. We just did a couple of them. Chapter 6, very interesting. Okay. That's stuff we can relate to, and we don't know the answer. It's like you got to calculate it. I'm sorry I was a little bit not focused today, but somehow that other classes. I don't know. I'm just back to back 2 different. It's like playing one kind of music and then another. I don't know. Just I can't flip a switch like that. Maybe maybe you guys can do it. I can't do it.
Yeah.
I prefer to have transition time, even if it's just walking from class to class. I'm a little sad that I'm graduating now because it's like, well, I'm done.
Not really.
So,
I want you to come back for a master's. So I don't know. Are you willing?
Well, I mean, that's true. I am gonna probably get my master's degree at some point. So at least that.
It doesn't have to be here. You could get it.
Anywhere. Yeah.
I forget. Where are you living in Santa Clara? What?
No, I'm in Burbank. So genuinely, CSUN is the closest school for me. I mean, we technically have a private college in Burbank, but I don't care. I wanted to go to a public university. So yeah, I just needed something that's close enough to drive and it isn't miserable and the parking isn't terribly expensive. So UCLA and USC are awful for that.
Well, actually, USC has something, right? We both know you're interested in secondary teaching, or you sort of said maybe.
I thought they had a fantastic teaching program.
I talked to somebody, and they said, "I'm telling you, I'm not making this up." They said that the USC covered everything for that program, everything. So, yeah,
that would be helpful. But yeah, I know in a lot of cases, it's required that you teach in LA for a while. I don't necessarily want to be tied down to LA.
I don't believe that would apply to USC because USC is private. That would be that would be contradictory to their nature. But you know what? I think, in my own opinion, is you should probably get a master's here. You know what I mean? Even if you're going to be a high school teacher, I think I don't think I know you should do it. I don't have any grants, but some people have grants where they can fund student research. And a little bit of money makes it a lot more serious.
Right, yeah.
Were you there at the open house when the teacher said that, when the instructor?
Mm-hmm.
They were getting $2,000, right? I said, $2,000, yeah, they can perk up a little bit, perk up,
Right.
See, yeah, okay, now I'll do it, So there have been some grants in the past that were big cash, and we're talking $10,000, for a month. So big, that's tax free. I think, you're not being paid to work. You know what I mean? So therefore,
right, it's for research.
Yeah, the same thing.
For granted.
If you're a grad student and you get a fellowship, no tax. If you're a TA, tax. If you're paid, if you're not, how to say it, if it's a gift and you're not required to work for it, not taxable. In general, I don't want to don't quote me, because somebody gets. Yeah, but I think the way the master. Actually, I cut you off, Amy. You were saying something. I'm sorry. You were going to say something.
No, you're fine. I'm just trying to find a good. My main thing is I'd like to get a teaching job sooner than later. So my plan is more to just do my master's as a night program. So, I'm living with my parents right now. I'd like to not be living with my parents for a bit.
Come on, man. It's not like you're. You know what I mean? It's not, this shouldn't be in other countries in the world, other, societies.
Oh yeah, no, it could be very different, but yeah.
This is, that shouldn't be, I mean, it's cool that your parents allow you to, I mean, it's actually, they won't be around forever, so you spend some more time with them. I don't know. I feel like this, being old, I think there's a benefit, there's a good aspect of staying around the house, So yeah, I don't think that's any. I mean, you're saving on rent too. I mean, think of all the money.
Yeah.
Well, yeah. So, I don't know. I'd still like to move out if I can and get a big kid job for a little bit before going.
We have TAs here. We have TAs.
Yeah.
That pays money.
Mm-hmm.
I don't know what it is, but it pays. I just guessing 20,000 a year at least. I don't know.
Mm-hmm.
We got that. They somehow.
That's still not enough to move out in this economy at this point. At least not in Los Angeles.
Well, okay. I was a TA at USC, so and at UCLA, so I know that they're probably up to 40,000 now a year. I can just and they cover your tuition. So yeah, no, they don't expect you to be. If as a TA you might work 15 hours a week. You're supposed to technically work 20, but of course I didn't do anything. But you're supposed to work 15 hours a week teaching, and it takes the weight off the professors. You're doing the grunt work and probably most of the teaching. So, but there won't be any money coming out of your pocket if you become a math TA. And if you go to med school, yeah, you got to pay for that, right? But not for mathematics.
That's pretty cool.
No.
Well, I'll see you later, Professor.
All right,
Take care.
see you
Thanks.
later, Ann.